Consider the following statement. If A is a square matrix with a column of zeros, then A is not invertible. And we want to figure out if this is true or not. Now, a square matrix is a matrix that is n by n, so it has as many rows as it has columns. So just so that we can understand what we're talking about here, here are examples of square matrices with a column of zeros. So of course, if we're dealing with the 1 by 1 matrix, then in this case it's just the number 0. And 0 has no inverse. It has no reciprocal, right? Because remember, right, if 0 would have an inverse, I would be able to multiply 0 by something in order to get 1. The 1 in, maybe if we want to convert those into matrices, we're going to get the 1 by 1 identity matrix, and that's not possible, right? 0 times anything is always going to give me 0. So clearly, at least, if the matrix is 1 by 1, it doesn't work. So as far as the statement's concerned, you could actually say already it's false, because it's false if n is 1. Okay, but I'd like actually to investigate this a bit more deeply and see if it can be true actually for maybe some n's. If we've got a 2 by 2 matrix, okay, it could be that matrix, but in general, right, if I've got a 2 by 2 matrix, okay, A, to be able to say that it's invertible, I would be able to find some matrix B that would also be 2 by 2 in order to get the identity matrix that's 2 by 2. We just call it I2. Okay, and similarly, this matrix B would be such that BA would also give me I2. So this is by definition of invertibility. So if we can't satisfy this any of these two equations, right, we're done. We won't be able to find an inverse. So I'm not going to work with a specific example, right, because that wouldn't just give me like the answer for that specific example. I want to work with something very general. So maybe I'll start with the case n equals to 2. Maybe I could first state what I concluded from n equals 1, not 0. If n is 1, it is not invertible, since 0 has no reciprocal or inverse. Okay, and the reason for that is 0 times anything is always equal to 0, and it's never going to be equal to 1. If n is equal to 2, okay, all right, maybe we can focus on a kind of specific example. Maybe we can look at the case where the first column has zeros, or maybe the second column, why not? Okay, and if we can come up with a reasoning that's general enough, and that doesn't not really depend on the fact, well, that can be adapted if to matrices that have a different column that has all zeros, then we're good. So we're going to assume the second column so as zeros. So let's assume that the second column has all 0 entries, or that the second, maybe I should have said the second column is a column of zeros. Okay, so that means that A would be some matrix with some column. I'm going to call that A1. Maybe I'll put that in bold because it's kind of like a vector. Right? It's the whole column and column 0 like that. Okay, I'm going to put that in bold too, since it's a vector. And now what I'm going to try to show here is that if I'm going to show, let's show that if B is a matrix, then BA equal to I is impossible. So when I write I here, right, it's I2. I should have said B is a 2 by 2 matrix, of course, is impossible. So that's not possible. There's no inverse, right? I need BA and AB equal to I. I'm just going to try to show that BA is actually equal to I is actually not possible. Now, B times A, well, what is that? That's B times the matrix A1 being the first column of A, 0 being the column of zeros. And I don't know if you remember, when we multiply a matrix by another matrix, we can actually decompose it into the product into the columns, so that to get the first column I need to multiply B by the entire first column of A. So that's the first column of BA. Now the second column is B multiplied by the second column of A, like that. Now B times 0, right? It's all 0 entries, right? So if I do my matrix multiplication, you multiply anything by all zeros, you're going to get 0 again. So this is BA1 is some column with potentially zeros or non-zeros, who cares? But the B times 0, right? So imagine B is, I don't know, let's say 1, 2, 3, 4. You multiply that by 0, 0. Clearly you're going to get 0 again, okay? And that's independent of what B is. So if B has any numbers here, you're clearly going to get 0. So this is all zeros, okay? And could this be equal to I? Well, no, because look at this column and that column. Like, this is the column of all zeros, and the second column of I2, right? This is I2. It's not a column of all zeros, right? It has a 1 in there. So since 0, which is the column matrix of all zeros, right? This is not equal, that clearly is not equal to 0, 1. Then BA equal to I2 is impossible. So I write I2, but it's clear from the context that it's I2. So you can you can write I2, or you can just leave I like that. Okay, it doesn't matter. I'm putting I2 just so that you can follow more easily. So therefore, A has no inverse. And then a similar reasoning would hold, right? If it would be the first column of A, which has all zeros. Okay, so I'm going to write that. So a similar reasoning, let's move that up, holds if the first column of A is a column of zeros, so I'm gonna let you take care of the case n equals 3. Okay, follow a similar reasoning and you'll see that you can't have an inverse. Okay, so this is your turn. Okay, and maybe write a statement like n equals a positive integer. That's also your turn. Try just to maybe write something that shows that in general you have no inverse. So this is actually a result you should remember. If maybe we can frame this, if there is a column of zeros, then the matrix has no inverse. So for 1 by 1 matrices, like 0 is the only one, the matrix 0 is the only one that has no inverse. But for 2 by 2, it's very easy now to construct examples of matrices that have no inverse. As soon as you've got a column of zeros, you're good, right? So all these matrices, they're not equal to the zero matrix, but they're not invertible. Now what I want to do is show you a second solution. So this is like solution 1. I don't know if I wrote solution 1. This is solution 1. I want to show you a second solution that's based more on geometry. And there's some concepts in there that we're going to reuse later on. So just to make my argument simpler, okay, I'm going to assume n is 3 and that, let's say the second column is the column of zeros. But you'll see that, again, my reasoning is can be adapted if n is some other number and it's a different column that has all zeros. Okay, so let's assume that n is 3 and that the second column has zeros. Okay. So that means then our matrix A would be, you know, something like, I don't know, A11, A21, A31. Those are any number, okay? Second column has all zeros, and this would be A13, 23, 33. Okay, that's my general matrix A here. And now I'm going to look at that as the standard matrix of a linear transformation. Okay. So let A be the standard matrix of a linear transformation. So it's the standard matrix of a linear transformation T. It's going to take points or vectors in R3 and output vectors or points in R3, right? Because when I do T of x, right, that's going to be AX, but A is 3 by 3, so the X has to be 3 by 1, so that's why this guy here is in R3. And when you do a 3 by 3 times a 3 by 1, you're going to get another 3 by 1 output here, okay? Actually, this is going to be 3 by 1. So this is again in R3. So that's why it's from R3 to R3. So we're mapping, right, from this space to that space, right? So we're in 3 space here. So just so that maybe to illustrate this again, you've got X, which is in R3, and it's going to be mapped through linear transformation. Maybe we can call it TA, like that, because it has standard matrix A. It's going to be mapping that onto something that's also in R3. But let's take a closer look at what is that set. Okay, A times X. So I take any point X in R3, calculate AX for all of them. What's going to be that set, the set of points that I can possibly get in the output. Now AX is what? Okay, so AX is, it's going to be A11, A21, A31, 0, 0, 0, A13, A23, A33, and I multiply that by X1, X2, X3. Now this guy here, right? So imagine that this vector is the vector 1, 0, 0. Okay, if you multiply matrix A by 1, 0, 0, you're going to get the first column of A, right? That's because as you multiply, maybe I should write this more explicitly, as you multiply, right, you're going to get, one way to look at it is that you're going to get a linear combination of the columns of A, like that, right? But if I've got 1, 0, 0 for the components of X, you realize that we're going to get just the first column of it. We're going to get A11, A21, A31. So that's why, and I've mentioned this many times, this is actually, this first column is T of I, right? It's I being this vector, right? So if you apply T to I, you get the first column This column here is where j gets sent. That's t of j. That's t of k right there. So what I really get here is x1 t of I plus, this is always going to be 0, right? Plus x2 t of k. So what is that? That's t of I. I don't know what it is, but it's going to be a vector, right? This is also some vector. This is a linear combination, right? This what I get here is a linear combination of two vectors. Okay, so what's a linear combination of two vectors? Right, essentially you've got where, I don't know, okay, we've got our two vectors like this, and a linear combination is going to give us some sort of, you know, I don't know if you see it, but it's going to give us points that are in a plane if those vectors are linearly independent, if they're not parallel. So if I've got vectors here, that could be like t of I, t of j. If they're not parallel, I'm going to be generating points in a plane passing to the origin. If they are parallel, if they're actually one top of each other, so if that could happen, I could have like t of I here, t of j there, then I'm going to get points on a line. And maybe there's an even worse case where t of I and t of j are both 0, in which case I'm just going to get the origin. So in other words, my output, okay, is going to be a vector or a point, if you prefer, that's part of a plane, that's part maybe of a line, or that's just a point. Okay, those are all the possibilities that I can get. I can't actually generate points in all three space. Okay, the highest or the largest possible set is actually this set, a plane. So I can write this here. The image of R3 so not of R3, but the image of the function. So the image of t, maybe I'll write t of a, is either a plane, a line, or a point. Okay, or maybe if you want to be even more explicit, that's ti not parallel to t of j. A line would be the case where t of I is actually parallel to t of j. Not t of j, t of k. And a point would be when actually t of I and t of k are equal to 0. So this is t of I equals t of k equals to 0. Okay. But my point here is that we're going to be mapping on a set that has at most dimension 2. Right? The plane has dimension 2, line dimension 1, point dimension 0, which has at most a dimension of 2. So maybe to recap here, I've got t of a. We're in R3 here, right? It takes some vectors in R3. This is a set clearly of dimension 3, and it's going to be mapping on a set here. Okay, so AX will be right. So this set here, AX, well, all the points AX, right? So will be a set of, this is going to be of dimension less or equal to 2 at most. Okay, so I won't be able actually to take this set and send it back into R3, into a set of into R3, all of R3. So I'm not able with there's no linear transformation. So if I'm looking for a linear transformation B that takes a plane, a line, or a point, I won't be able to map this plane, line, or point onto all of R3. That's impossible. This is the note I wrote before. So we will not be able to find a linear transformation that maps a plane, well, maybe I'll write a set of dimension 2 or less onto R3, which has dimension 3. So because of this, right, I'm not going to be able to go back to where I initially started, right? So that means here, right, if I do BAX, I'm not going to be able to get X for every X. Right? This X here is in R3. If I do AX, that's now going to be either on a plane, a point, it's going to be on a plane, a line, or it's going to be a point. If I do B of all those vectors AX, I'm not going to be able to get back all vectors that are part of R3. So that's the idea here. So the BA will never be, right? So to have this true for all X in R3, right? This has to hold. That would mean that BA would have to be the identity matrix, the thing that does not change X. But that's not possible. Okay, so I'd have to have B equal to X, but that's not going to be possible. So therefore, it will not be possible to find a matrix B such that B times A is the identity matrix. So that's the idea here with linear transformations. It looks complicated, but I'm going to use this argument later on. So as soon as you've got a linear transformation that reduces the dimension of the space, there's not going to be an inverse. So A here, our linear transformation, A it basically squishes R3 onto a plane, a line, or a point. And then you can't go back and unsquish that point, that line, or that plane to get back R3 again. So this is what you should take away from this argument. Okay. Now, of course, if you're gonna argue on when you do the exercises, you want to use solution 1. Okay. You don't want to use solution 2 unless you think solution 2 you understand it well. But I know that for most of you this is not easy to grasp. But this is what you should take away from this exercise. Okay, if even if you have trouble following everything, just remember that if you've got a linear transformation that decreases the size, the dimension of the space, it won't be invertible. You won't be able to go back to where you were through another linear transformation. Okay. And finally, I'm not gonna write it down, but you know, if our matrix A has you know, maybe it's if the third line now, a third column now is a column of zeros, well, you'd still have like a linear combination of the first 2 columns of A. Okay, so the image would still be maybe a plane, a line, or a point. And then if you've got a matrix that's of larger size, maybe let's say it's a 4x4. If there's a column of zeros, it means that there's well, in this case you'd have what, like you had ijk and some other elementary vector, like maybe w would be 0 0 0 1. Okay, and anyway, the point is that one of them is actually, if there's a column of zeros, one of them is going to be mapped onto 0, so you're going to squish R4 onto a space of lower dimension, maybe of dimension 3, 2, 1, but it's not going to be of dimension 4 again.